So let's take a look at the first one here. Solving the equation. We can simplify each side of the equation separately and then come back and start to solve it. On the left side over here, the parentheses, there's nothing we can do inside of them. So what do we have to do to them? Multiply by the 2. So 2 times 5x is 10x. 2 times negative 7, negative 14. We still have the plus 4 there, which is going to turn this into 10x minus 10. Negative 14 plus 4 is negative 10. On the other side, again, nothing to do in the parentheses. So what do we do to them? Times 5. So 5 times 3x, 15x, and 5 times negative 2. Negative 10. Now we still have the negative 5x on the end. What does that turn it into? Positive 15 and negative 5 make 10x. And we still have the negative 10. Well, we go to solve here. What happens? Yeah, we subtract 10x. It goes away. We get negative 10 equals negative 10. Is that true? Yeah, it is true. This is one of those rare occasions where the variable disappears in the equation. Since what we get here is two numbers that are actually equal to each other, what that is saying is you can put actually any number in there for x and the equation will be true. If you had two numbers that were not equal, then no matter what you put in for x, there's nothing that'll make it true. I won't do that to you on a test, just so you know. You would really have to upset me between now and the next test to make me do that. Speaking of tests, by the way, if you didn't catch it, if you came in late, the test that you got back, you can redo the problems you got wrong and turn those back in. My deadline is usually the next test. So your next test is 2 weeks from today. So September 6th is your next test. You are allowed, by the way, when you correct those problems, you can work with your classmates. You can come to me and I will sit down and work through them with you. I have two goals to do that. One is to get you some points back. And two is I want to make sure you've seen the right answer and you have it down on the paper so that you know what, if you see it again, you have a better chance of knowing what to do with it. Okay, so this one, I hesitate to put it out there because I know you guys are struggling with these yet at this point because we only had about 20 minutes to talk about them last class. So let's see how much you remember. Well, the way I organize these is you have the ingredients, and that's just my word, ingredients, inputs, whatever you want to do, the things that you have on hand that you're going to be mixing together. And you have a certain result that you want to get over here. Well, our ingredients are what two concentrations are we mixing together here? 13 and 22. And we're going to mix those to try to create 19%. So that's the first part, is the ingredients. The two things that you are mixing need to go on the left side of the equal sign. The result that you want to get needs to go on the other side of the equal sign. Now, the next thing we have to deal with is the amount, whether it's a volume or a mass. In this case, I use milligrams, so it's a mass. The two amounts have to add up. The amount of the first ingredient plus the amount of the second ingredient has to equal the amount of the result that we're going to have. So what amount do we have in this problem? The 120. Which concentration does that go with? The 22%. Because we have that relationship where the amount of the first one plus the amount of the second one has to equal the total amount. It would be easiest here if we let this amount, the amount of the 13%, be our variable. So then the amount of the result is just going to be found by adding these two amounts together. X plus 120 is just X plus 120. I'm going to pause. Any questions so far? So then once you get to that point, it's just a matter of then translating it into the equation. The concentration for the first one, 13%, is going to become 0.13 times the amount of X plus the concentration for the 22% will be 0.22 times the amount of 120 equals, what's going to go on the other side? 0.19 times the amount of X plus 120. That's the hard part. Once you get here, most people have an easier time solving the equation. Now I'm going to reduce like we did on that first example here today. I'm going to reduce each side separately if I can. Nothing I can do to the 0.13x, but I can combine 0.22 times 120. What is that, 26.4? That's all I can combine on the left side. So now on the right side, the 0.19 has to multiply through the parentheses. So 0.19 times x is 0.19x. 0.19 times 120 is 22.8. Good. Now we've simplified, we've combined everything we can combine. We have to start to solve. But we notice there's a variable on each side of the equation yet, so we need to get rid of one of them. It's going to be the smaller one. So we subtract the 0.13. Now I get asked, what if we decided we wanted to subtract the 0.19? We would still get the same answer. It's just we'd be working with a lot of negatives in the equation. So the only reason I always subtract the smallest one is so I can avoid working with negatives as much as possible. So the 26.4 is on the left side all by itself. On the right side, 0.19 minus 0.13. 0.06x. Good. Plus our 22.8 yet. Now what? We're going to subtract the 22.8. Good. Which is going to leave us with 3.6. And then divide by 0.6. Or 0.06, I should say. Which is 60. So x is 60. Now we do have to make sure we go back and answer the question. The question was, how much of the 13% solution? Does x describe the amount of the 13% solution? Yes, it does. This was in milligrams, so this 60 is also going to be in milligrams. So it's 60 milligrams of the 13% solution. Any questions on that example? Okay, we are going to do a couple more examples of it. So. Now, one abbreviation we're going to use in here is the abbreviation NS. The NS could stand for a couple of different things. Basically, what NS is it's sterilized water. It is a totally inactive ingredient. It's what your medication would be dissolved in. NS can stand for normal saline or neutral solution. Either one means the same thing. There's no medicine, medical value to it. There's no medicine to it. It is just the vehicle that carries the medicine into a patient. So when you see how much NS, think sterile water. So how much NS would you mix with 240 milligrams of 18% solution to dilute it to, oh, let's go 12%. So again, we have, and again, I call them ingredients. You can call them the mixes or whatever you want to call them. The inputs, and then the results are what we're going to end up with. Here's a little bit trickier to find the ingredients. We have the 18%, but what are we mixing with it? Nothing, 0%. That normal saline or sterile water has no medical value, so it's a 0% concentration. And we're trying to get a result that is 12%. What amounts do we have? 240 of the 18. So it's best if when we have one of the ingredients, it's always easiest if the variable is the amount of one of the ingredients. So we're going to put X there as the amount of the 0%. So then the amount of the 12% is 240 plus X or X plus 240, either one. So now we can create our equation off of that. So we have the 18% is the 0.18 times 240 plus 0% is going to be 0.00 times X. Now I get asked, do I have to have this piece in here? You don't. It doesn't affect the equation. I just put it in because I like to have that same process that's repeated. It's obviously going to disappear in our next step anyway. So that has to equal 0.12 times 240 minus X. So, plus X, I'm sorry. So we go back to combine things here. 0.18 times 240. 43.2 works for me. 0 times X, of course, is just 0, so that disappears. On the other side over here, 0.12 times 240 is what, 28.8? And 0.12 times X, 0.12X. This one's actually not so bad to solve. Where are we going to start? Minus the 28.8. So what is that, 14.4 equals 0.12X. And then divide by 0.12. 120, you got it, equals X. So we get 120 equals X. We do need to make sure we go back and be sure that we've answered our question. So X equals 120. We're asked how much neutral solution or how much normal saline. That is the 0%, and X is describing how much of that we have. So it would be 120 milligrams of that is what we're going to need to add. Any questions there? Yep. As long as you write 120 milligrams in the answer spot, that's what matters. There might be some people that have different ways of doing this. If you did these in chemistry, there's something called the lever method that you can use for it. I'm not a huge fan of it, but it works. It goes off of the difference from where you're at to where you want to go. So there are other ways of doing this. I'm not one of those people that make you have to do it my way. I think this is the easiest way, but that's how my mind works. Other people might work differently. Yeah. Yeah, you'd probably lose, like if it were a 5-point question, you might lose 1 point for not having the units on it. The only way I don't grade for units is like if the question actually asks, how many milligrams do you need? Well, if it's asking how many milligrams, just putting the number there is good enough because it's applying the units. Okay, how are we feeling about the mixture problems? You guys want to see a couple more examples? Or are you ready to move on? More examples? Okay. This one. How about this one? How much pure alcohol? Yeah, that question can go in a bad direction fast, couldn't it? How much pure alcohol does it take to recover from a math for health professionals test? If you have to stop at the liquor store on the way home, mention my name so I get my kickback. How much pure alcohol should you mix with 180 milligrams of 38%? That ain't going to work very well. Let's go 36% alcohol solution to create 30% alcohol solution. I'm going to give you guys about 3 or 4 minutes just to get the equation set up. If you can solve it in that time, great. But the big goal is to get you to where you can set up the equation or whatever method you want to use to solve it. I'll give you a few minutes, but let's just take a peek. The ingredients that we are mixing here, we're mixing the 36%, of course, and pure alcohol is 100%. To get a result of 30%. The amounts we have, well, what do we have? 180 milligrams goes with the 36%. So we'll let the amount of the 100% be X. The amount of the 30% will be 180 plus X or X plus 180, either way. So the equation, .36 times 180. 100% is just going to be 1 times X. That's a plus 1, yes. Equals 0.30 or 0.3. Perfect. And then the 180 plus X is the amount in the parentheses. So I'm going to pause there again. Questions on where that equation came from? Okay. Obviously, seeing the 100% for the pure alcohol is the tough part. It's possible. You can ask me, yes. I will definitely answer questions on the test. So anyway, 0.36 times 180 is what, 64.8? 1 times X is just X. 0.3 times 180 is 54. And 0.3 times X, 0.3X. Now what? Well, we should get the X's together first. Subtracting 54 would work, but we're not really sure which side we want to get rid of yet. So let's get rid of one of the x's. Let's get rid of the 0.3x. We'll subtract that from our 1x on the left side. 0.3 minus 1 is 0.7x. That's 64.8 plus 0.7x equals 54. Once it's in this form where the variable only appears once, it's a little, we would still be able to solve it if you had subtracted 54, it's just there are going to be extra steps in there. Now that we have the variable all together, we can solve it with the fewest steps possible. We are going to, what went wrong there? Something was really ugly there. Oh, that ain't going to work, is it? I screwed up because I put in the pure alcohol, but I tried to lower the percentage. You can't add pure alcohol and lower the percentage. It's going to raise the percentage, isn't it? So that one can't. We set up the equation. That's good. But we can't solve it. So, sorry about that. That's my strike one for the day. How's that? Let's try one more example at least. Let's do one that'll actually work. How much 62% solution would you add to 360 milligrams of 44% solution? To create let's go 48% solution. Again, I'm going to pause for a couple minutes, let you guys at least get the equation set up, and then we'll go from there. So let's see if you got the equation set up right. What are the two concentrations that we are mixing here? 62 and 44. Does it matter what order we put those in? No, not at all. The result is going to be hopefully 48. What amounts do we know? 360 goes with 44. So we'll let the amount of the 62 be x. The result is going to be x plus 360. So then our equation will be, somebody talk me through it. Okay. Yep, that's okay. Times 360. Perfect. So on the left side, our ingredients, we got 0.62x and 0.44 times 360. It doesn't matter which one of those is first or second, as long as they are added together there. Then what's on the other side? 0.48 times the x plus 360. Good. And now we just have to solve the equation. So on the left side, there's nothing to do here on this first one, so that's just 0.62x. 0.44 times 360, 158.4. Okay, equals 0.48x, good, plus 172.8. Okay. Perfect. Now we've got an x on each side, so we're going to get rid of one. We'll subtract the 0.48x. 0.62 minus 0.48 is 0.14x. Perfect. So 0.4x plus 158.4 equals 172.8. We'll subtract the 158.4. Good. So 0.14x equals 14.4, yep. So we'll divide by 0.14, yes. Which gives us x equals 102 point what? 0.8685, okay. There it is, milligrams. And that is the amount of the 62%, which is what we were looking for. Hopefully you're building a little bit of confidence with these. It's just a process, a matter of doing them, getting used to it, organizing yourself. I'm big on making tables to organize problems, as you've probably noticed in the last few weeks. Okay, well, our next thing we want to look at is we're going to be looking at using these formulas, using equations for other things. We've solved equations, we've used equations for solving word problems like that. We want to look at other uses of variables. You know, variables can hold that unknown value in the equation, but it has a value, we just haven't figured it out yet. We don't know what it is yet. Well, variables can also be used to hold a place in formulas. So you might have a formula that is, well, something simple like P equals 2L plus 2W. This is the formula for the perimeter of a rectangle. And in a formula like that, there are a few things we can do with it. The first thing we're going to do is something called evaluate. And what evaluate means is to give a value to. In order to do that, we have to be told the numerical value for all of the variables except for one in that formula. What's that? We could get the P, the L, or the W, any of the letters. So there's three variables. I have to give you the values for at least two of them. So if I tell you that L equals, in this case, L equals 8 and W equals 5. We could calculate P then by putting those variables in. So P is going to be left there. We don't know its value. 2L is going to become 2 times 8, right? Plus 2W is going to become 2 times 5. And now it's just a matter of order of operations. What would we have to do first here in trying to combine those? Multiply the 2 times 8, which is 16. Then we'd multiply the 2 times 5, which is 10. And yes, we can add them together. 16 plus 10 is 26. Other formulas that are important to us might be I will use P for pounds. I know that's not correct. We go P equals 2.2K. In other words, pounds equals 2.2 times kilograms. If I tell you that P is 198 pounds, well, we can find K by putting 198 in where the P is. Now, there's nothing to combine here, but we do have to solve for K by doing what? Dividing by 2.2. We get 90. Very good. 90 equals K. So that would be 198 pounds would be 90 kilograms. You might be given something like this. Your Fahrenheit temperature is 9/5 times your Celsius temperature plus 32. together. If I tell you that the Fahrenheit temperature, 98.6, hopefully you guys recognize that one. Human body temperature, yeah. What would that temperature be in Celsius? I'm going to give you guys a second. Plug that in and figure it out quick. Let's take a look. This one's a little tricky because I decided to be mean and combine decimals and fractions together in the same problem. To solve this, to get c by itself, we would subtract 32. So 66.6 equals 9/5 c. Okay. Yeah, dividing by 9/5 is the same as multiplying by 5/9, right? So yes, we can either divide by 9/5 or multiply by 5/9, either one. So you get the same result. 66.6 times 5/9 is 37. It comes out to be. So human body temperature is 37 degrees Celsius. Now, chances are we're going to do more converting from Fahrenheit into Celsius. Everything is switching over to metric. And we're going to be taking things that are in standard units and switching them to metric. So rather than putting the Fahrenheit temperature in here and having to solve this equation every time, it would be nice if we could rearrange that equation so we just plug in the numbers into order of operations. It'd be nice if it was C equals. Well, we can do that. And we can do that by following the exact same steps we just used when we put a number in for Fahrenheit. First thing we did was subtracted 32. Then we either multiplied by 5/9 or divided by 9/5, either one. So we'll do the exact same thing here. We're going to subtract 32. That 32 is gone. We do have to subtract 32 on the other side. Well, what is f minus 32? It's f minus 32. On the right side, all we have is the 9/5 c. Now, just like before, we have to either divide by 9/5 or multiply by 5/9. I'm going to multiply by 5/9. So that's gone over there. On the right side, all that's left is c. On the left side over here, 5/9 times f minus 32 is just 5/9 times parentheses f minus 32. These two things are equal to each other. I can switch their sides. If you think of that balanced scale idea, it doesn't matter which side they're on, they're going to balance each other. So most people would look at that and say it's a lot easier to think about it as c equals 5/9 times parentheses f minus 32. So let's say that we have a temperature of 87 degrees Fahrenheit. Oh, let's go. This is going to work a little better than that. Well, let's say we have a temperature of, let's do 77 degrees Fahrenheit. Will work a lot better for us. We want to convert that into our Celsius temperature. We're going to put 77 in where the F is. And now it's just order of operations. What do we do first? The parentheses. 77 minus 32 is 45. Then we're going to do 5 ninths times 45, which is 25. Where did I lose you? Good question. You make that 45 over 1, right? That's why I chose the 77 degrees, so that would cancel out. 9 and 45 both divide by 9, giving me 1 and 5. So 5 times 5 is 25. 1 times 1 is 1. Any other questions? Well, the problem with that is 5 ninths. It's 0.555555. Oh, it's 0.5 repeating. If you're familiar with that notation, little bar, that means repeating. So to turn it into a decimal, it doesn't work as well. You're gonna end up with round off error on it. So it depends on how precise you want to be with your calculation. Okay, it is time for a break. It is 11:21. Let's come back at 11:31. We'll look at a couple more examples of rearranging the formulas, and then we'll move on. So we rearranged that one formula for the temperature. Let's look at some other formulas and rearranging them just so we can get a little bit of practice with it. Now I'm going to go to a typical generic equation like this with no numbers in it at all. Let's say I want to solve that for the variable x. So just like if there were numbers in there for a, b, and c, I have to get x all by itself. So what I'm going to do is I'm actually going to give an example here where there are numbers for a, b, and c. And we're going to parallel the two problems. Over here with the numbers in it, what would be the first thing I would do to try to solve that? I would subtract 7. Very good. That would make that 7 go away, leaving me with 3x. Over here, 19 minus 7 would be 12. Well, over here with all the variables, the parallel move to that, the equivalent move to that is to subtract b. So it's gone over here, leaving me with ax. Now, a big difference is on this side, we could actually do 19 minus 7. C minus b is just going to be C minus b. Just trying, if this is confusing over here, you can just ignore it. It's a matter of just getting the variables by themselves moving around. Over here, of course, the next move would be to divide by the 3. Yep. On the left side over here, what's the equivalent move? Divide by a. So that a is gone, leaving us with x. Now this is why I do my division like this as a fraction, because that's exactly what this is going to turn into. It's just c minus b all over a. The number we're dividing by becomes the denominator of a fraction. Let's do one without the parallel equation, so it makes it a little easier on you. Let's talk about something like this, and let's solve it for b. This one's a tough one to rearrange. But before we rearrange it, we have the parentheses here with the h outside of it. Inside, but we got to ask, is there anything we need to do inside that parentheses And in this case, there is. We have that b plus c, and it's over 2. Well, okay, somebody had an idea over there. What is it? You could multiply everything by 2 and get rid of the division. That works. If I multiplied both sides by 2, I'd end up with 2a equals b plus c in the parentheses plus h. That would work. Now we're trying to get b by itself, so we have to get rid of h and c. We can keep going on the track we are. What would be the next step? What would be the next thing to get rid of? Okay, good question. If I remember, I'm multiplying the whole side by 2. What's going on the right side is I multiply by 2. Let's write it out. As I multiply by 2 on each side, obviously the left side is just a times 2, is 2a. On the right side, what is happening, since these are multiplied, h is multiplying that, I can think of this as 2 over 1 times b plus c over 2 times h over 1. I'm just turning the h into a fraction to make it h over 1. The 2's cancel out. It's like multiplying 3 fractions together. I can cross cancel the 2's. They're gone. I still have b plus c in the parentheses times the h over 1 or times the h. Okay, so now do we get rid of the c or the h first over here? Well, here's the thing. Remember when we first started solving equations last week, we asked ourselves when this equation was put together, what was done to the variable? So in this case, what would be done to b? The first thing that would be done if b were a number is c would be added to it because it's in parentheses. And then the next thing that would happen is that result would be multiplied by h. When we take it apart, we have to go backwards. We reverse the steps. So the last thing that was put on this was multiplying by h. So that's the first thing we have to take off. We're going to divide by h. 2a divided by h is just 2a divided by h. On the right side, the h's divide out, and we're left with b plus c. And all we have left is subtract. Notice I took out the parentheses because there's nothing else there on the right side anymore. So yes, we can just subtract c. On the right, all we have left is the b. 2a over h minus c is 2a over h minus c. Yeah. Let's do a little bit easier formula for you. How about this one? P equals v squared over r, and we're going to solve it for v. For v. So v is on top of the equation right now, which helps. So we're going to multiply by r to get rid of the r. So you got PR equals v squared. Now this is something we haven't run into yet, but what's been done to v here? It's been squared. So to get rid of it, we would square root it. So the left side is going to be the square root of p times r. Square root and squared cancel out. That's just v. Okay. Like I had said on that first example with the temperatures, like here, if I'm looking for the V stands for voltage. If I'm looking for V and I know P and R, I could just put in P and R and then I could solve the whole equation for V. But if I'm going to have to do it over and over again, it's a lot easier to rearrange the equation like this so that when I give you P and R, you just put in those numbers, multiply them in square root, and you've got the result instead of having to solve an equation. So it's just a matter of speed. If you're only going to do it once, let's do this. Let's say that P equals 3 and R equals 27. If I'm only going to do that once, yeah, by all means, I would have my P equals V squared over R. All I would do is put in 3 for P and 27 for R, and I would solve the equation. I would multiply by 27, so that's gone. 3 times 27 is 81. That equals V squared. And then I would just do the square root to get V by itself. Square root of 81 is going to be 9. So V would be 9. But if I'm going to do this over and over and over for different values of P and R, if I use this one over here, I'm going to rewrite it as V equals the square root of P times R. Well, if I take my P equals 3 and R equals 27, well, this is now really easy to do. All I have to do is multiply. Come on. 3 times 27 is 81, and square root to get 9. So it's a little bit quicker here. Again, if I'm only going to do it once, I'm probably just going to plug it in and solve it like I did over here. But if it's something I'm going to have to do a lot, I want to rearrange that formula to make it a little bit more efficient. That is a good question. I mean, why do you want to go through that trouble when the formula is already there? It's just an efficiency issue. You can still do it without. Now, your book likes to do some weird ones like this. But I want you to solve that for A. If I tried to solve this like an equation like I have been doing, this would be kind of a struggle. But we did those percents last unit where we'd have something like 30 over 100 equals 18 over X. How did I find X? Cross multiply and then divide, right? So 100 times 18 is 1800 divided by 30 is 60. X equals 60. If I am solving for A here, I can do exactly the same thing. Cross multiply. H times V is H times V. And then divide by M. So A would be H times V divided by M. There will be probably 2 of them. That's the biggest, that's exactly it. Just pretend they're numbers. If you have this equation like this, if you're given one like that, just pretend, okay, let's just put in numbers. Let's say 3, 5, 2, and A. Well, how would you find A there? You would cross multiply. You would do 5 times 2, and then you'd divide by the 3. Then just replace the numbers with the letters. You know, I had said taking a word problem and putting it into a formula, I believe, is the hardest part of math. Working with those symbols is probably in the top 3 or 4 hardest items to do. So if you're frustrating you, don't feel bad. I guarantee you, you're not alone. Okay, so the next thing we want to talk about in here is something called ratios. Ratios are actually a very powerful tool. The combination of ratios and proportions actually includes percents. Percents are a special type of ratio, is really the most powerful tool in math. I would say 90% of math problems can be solved with ratios at some level. All a ratio is a comparison between numbers. For example, right now, if I wanted to compare the number of students on the network to those that are face-to-face in the classroom with me. Right now we have, what, 1, 2, 3, 4, 5, 6, 7 students on the network, it looks like. And we have, what, 9 here in the classroom? So that gives me a ratio of 7 to 9. Now I can express that ratio just like I did with a fraction, 7 to 9. I can express it with a colon, 7 to 9. Or I could write it out as 7 to 9. I typically like to write it like this because there's a lot of things I can do with fractions or with ratios that are similar to what I can do with the fractions. For example, we could do, I'm going to take one of my other classes here just because it makes it easier. I've got a class that mixes CNC with woods. So let's take a ratio of CNC students to wood students. In that classroom, I have 8 CNC students and 12 wood students. So it's an 8 to 12 ratio. Now, to make it simpler to visualize, I can reduce that ratio just like I can a fraction. Both of those divided by 4, exactly. Give me 2 to 3. That's a 2 to 3 ratio. That is saying for every 2 CNC students, there are 3 wood students in that classroom. Now, there are things a little bit different about ratios than fractions, some things we can't do. Let's look at a different class I have. I've got broadband students combined with IT students. And I have 9 broadband, let's do it the other way around. I'm just going to make up numbers here. I got 15 broadband to 9 IT. I can still reduce that. Both 15 and 9 can be divided by 3. Gives me 5 to 3. So I still can reduce it. But I cannot take, right now it looks like an improper fraction. I cannot change it into a mixed number because a ratio compares 2 numbers. So it's 5 to 3, it's not 5/3. So I would have to leave it as 5 to 3 like that. Another example might be the tables that are in the classroom here. The tables in our classroom, 18 inches wide by 72 inches long. If I did a length to width ratio, well, the length is 72 inches, the width is 18 inches. You notice just like in fractions, I can cancel out. The inches cancel out. Both of those can be reduced. To save time, I'll tell you they can both be divided by 18. 72 divided by 18 is 4. And 18 divided by 18 is 1. If this were just a fraction, I would just write that as a 4. But it is still a ratio. We have to compare 2 numbers. So we would have to leave it as 4 to 1. You will notice in each of these ratios, I compared things that have the same label. Here it was inches to inches. These were all students to students in both of them. And that is one of the requirements of a ratio, is you must compare like things. So you have to compare things with the same label. Inches to inches, students to students, milliliters to milliliters, whatever. So if I had a ratio or a comparison of 2 feet to 18 inches, is that a ratio? No, it's not, because they're different units. Now, fortunately, we can change those units. I can make 2 feet into 24 inches. Now they're the same units. Now it's a ratio, and I can reduce. Inches cancel out. Both of those can be divided by 6. Gives me a 4:3 ratio. So what happens if we have two numbers that we need to compare that aren't the same units and we can't change them to the same units? Let's say we send somebody on a road trip and they go 365 miles in 7 hours. There is no way we can turn miles into hours or hours into miles. There's no way we can make these labels the same. Hope you feel better. Have a good week. This is what we refer to as a rate. So that's the first difference between a rate and a ratio. The ratio compared things with the same labels. A rate compares two different things, two things with different labels. The second is we can create unit ratios. This was a unit ratio. The denominator was 1. But normally ratios, it's okay to leave them as 4:3 or 2:6, 2:7, whatever. In a rate, we almost always express it as what's called a unit rate. We turn the denominator into 1. And the way we do that technically is we divide by the numerical value of the denominator. 7 is our number in the denominator, our bottom number. So we're going to divide both the top and bottom by 7. Well, 7 hours divided by 7 is just 1 hour. 365 miles divided by 7 is what? 52.142857143? Something like that? Miles? Something like that, right? Approximately. Well, depending on where we want to round it, let's say we want to go to 1/10 of a mile per hour. We'd write 52.1. And typically, I mean, this is a unit rate like that, but typically, once it's a unit rate, we write it so that the fraction is disguised. It's hidden in the units. So yes, 52.1 miles per hour, like that. So it's still a fraction. It's still comparing two numbers. It's just kind of hidden in the units. In fact, we often would disguise it completely by MPH. So the appearance of the fraction is gone completely, but we still have to remember that it is there. For example, let's say on this trip, we get 24 mpg. What does that stand for? Miles per gallon. So when we see something like 24 mpg, we have to think 24 miles per 1 gallon. Why that's relevant to you guys? Well, you might have you might have a IV that's flowing at 30 milliliters per hour. When to do any calculations with that, you have to realize that 30 milliliters per hour is 30 milliliters over 1 hour. That's the form it's going to be in for us to do any calculations. So since we're on rates, let's do some examples of medical rates. Let's not. Our dosage calculations that we're going to do in Unit 3 are mostly dealing with rates. So other rates we might run into 3 milligrams per kilogram. As, again, you have to think 3 milligrams of medication per 1 kilogram of mass. Yep. If there's no number, whenever there's a unit like this, where it's one unit slash another unit, yes, that second unit is on bottom and it has a number of one, a count of one. You'll run into other IV flow rates other than milliliters per hour. You might run into 1.8 milliliters per minute. And again, that's 1.8 milliliters over 1 minute. Another abbreviation I'm going to introduce you to, just like NS, GTT means drops. I have no clue where GTT came from for drops, to be totally honest. Very common, you might have 45 drops per minute on an IV. Again, you need to look at that and realize that is 45 drops over 1 minute. Ratios. Well, ratios, again, are everywhere in medicine. When you go to constitute a medication or anything like that, usually it's going to be in milliliters per milliliter because it's ratio. They have to have the same units because it's ratios. Usually it's going to be milliliters per milliliter. It could be milligrams per milligram. We might have 200 milliliters of alcohol. This is rubbing alcohol, so all that's going to do is make you blind and drive you crazy. Which might not be that different from math class. Who knows? 200 milliliters of alcohol in 500 milliliters of sterile water. So that ratio, 200 milliliters over 500 milliliters. Again, the units are the same. So milliliters cancel out. Both divide by 100. That's a 2 to 5 ratio. Now I'm going to go ahead. No, it's the milliliter, yeah. That's the label. I'm going to introduce you to a term that we're going to talk about a lot more in our next unit. A dilution is a ratio. We might have a 2 in 5 dilution. What that means is we are taking some sort of an active ingredient, like a medication. Let's say this is a 2 in 5 dilution of lidocaine in water. That's a 2 to 5 ratio. The 2 is the lidocaine, the 5 is the water. And because a ratio has no units in it, it doesn't matter what units we use. We could have 30 milliliters of sterile water. Want to know how much lidocaine we're going to take? Well, we can use that. The 5 is the water, so we're going to put the 30 on bottom because that's water. It's in milliliters. Now, just like we did with our percents, how would we find this number here? Cross multiply. Because the two ratios have to be equal, this is a proportion. So we'll do 2 times 30, which is 60, divided by 5 is 12. The units have to be milliliters because these are ratios. The units on top and the units on bottom have to be the same. Go ahead. Yes, you can do that. Yeah. And, getting that 6, what you're really doing is 30 divided by 5 is 6, then 2 times that. So it really is cross multiply and divide, you're just doing it in a different order. That is called a proportion, as we said, and that cross multiply and divide is the main tool for solving them. Excuse me, I'm fighting off a sneeze. My allergies are killing me today. Those proportions pop up everywhere. Now we might have, let's do one that's not medical here. Let's say that you are averaging 54 miles per hour, and you want to know how long it is going to take you to go 324 miles. Well, the key to using these proportions is to make sure we line stuff up, keep it together. 54 miles per hour, what is that going to look like if we write it out as a fraction? 54 over 1, what are the units going to be? Perfect. 54 miles over 1 hour. The nice thing about the rate is because the units are in it already, we know that on the other side, things have to match up. The top has to be miles, the bottom has to be hours. So where's the 324 going to go? On top. What do I do to find my hours? Cross multiply. 1 times 324 is 324. Divided by 54 is 6. So it'll take 6 hours to go that distance. And what if we have, let's say, a 2-in-7 dilution of iodine in water? How much water? How much water do you need to mix with 18 milligrams of iodine? Well, we're going to set up the ratio here. The 2-in-7 means 2 over 7. Here it's not units anymore, but what does it represent? We have iodine and we have water. Which of those numbers represents the iodine? The 2. Which of them represents the water? 7. So on the other side, when we set this up, the number that goes on top has to represent the iodine. 18 does represent the iodine, and it is milligrams. So what that means is what I'm going to get on bottom here has to be milligrams. Now I'm going to note a slight difference here. These proportions have to line up in at least one direction. Here, I have milligrams and milligrams there. They line up vertically, top to bottom. Up here, when it was a rate, it was miles and miles. This one lined up horizontally, so miles to miles that way, hours to hours that way. The units have to line up in at least one direction. In the rates, since the units are already given in the rate, you line them up side to side. In a ratio, since there are no units in the original ratio, the units you get in your second ratio have to be the same. Milligrams to milligrams, milliliters to milliliters, and so on. So to get that number, we cross multiply and divide. How many milligrams is it? 63. So it's going to take 63 milligrams of water. Now using that same dilution, how much iodine do you need to mix with 35 milliliters of water? Now you'll notice I did two things here. One is we're looking at the water now instead of the iodine, but the second is up here, we're talking milligrams. Down here, we're talking milliliters. Does it matter that I switched units? It does. But the ratio allows us to do that because the ratio has no units in it, 2 to 7. It's not telling us whether we're comparing milligrams to milligrams, gallons to gallons, or whatever. I have that 2 to 7 ratio. Again, the top is the iodine, and the bottom is the water. Pretend that actually looks like it says iodine. When I put in my water, my 35 milliliters, all that means is my units on top have to also be milliliters. Yes. They do have to have the same label within that ratio. Yeah, it doesn't, it can be water and iodine. It's just the units of measurement, exactly. It has to compare milligrams to milligrams or milliliters to milliliters. That is a good question. That can be confusing. So up here, because one of the measurements was given in milligrams, the other one came out in milligrams. Down here, since one of the units was given in milliliters, the other one is going to be in milliliters. 2 times 35 is 70. Divided by 7 is 10. So it'd be 10 milliliters. So that's one of the things that's flexible about a ratio. Because there are no units in the ratio, the units that we're using comparing to it can be anything. It's just once we have one of them, the other one's going to be the same. The milliliters would still cancel out. We'll talk about types of concentrations in the next unit as well. There are certain concentrations where you want to compare volume to volume, others where you want to compare mass to mass. Now, within each of these ratios, there are actually other ratios implied. Like here, I use the dilution here a little bit sloppily. But let's say we have a 2, I'm going to change my wording a little bit here. Let's say we have 3 out of 8. 3 out of 8 is implying that 3 to 8 ratio. Let's say that 3 out of 8 students will get an A in this class. Usually it's a little bit higher than that, by the way. So nobody panics. So in this case, we are comparing the A students to total. There's a second ratio implied. There's a second ratio implied in that. If 3 out of 8 get an A, that says don't. Yeah. How many don't get an A? 5 out of 8. The other piece. These are called complements. This computer's driving me nuts today. Complements are 2 things that add up to the whole amount. If we have a class, the students who don't get A's and the students who get A's and the students who don't get A's add up to the whole class. Now, for our ratio, this is going to be big in our next unit when we actually talk about formal dilutions, because the dilution compares the amount of medication to the total amount of solution. So we may have to, in many cases, look at its complement to see we don't know the amount of medication, but we know the amount of dilutant, and we can mix them together that way. Okay. I want to back off of ratios for now. We got one last little topic we've got to insert here before we're done this week. And we will look at it a little bit more next week. And it is place values. Give yourself a little bit more room here. We all know our place values, of course, ones, tens, hundreds, 1,000s, and so on. Let's say we don't. And of course, on the other side of the decimal, it's the 1/10ths, the 100ths, 1,000ths, 1/10,000ths, and so on. Well, we have what is called a decimal. Why am I P and L letters have been disappearing on me all day? We have what's called a decimal numbering system. That means base 10. What that's talking about is exponents. An exponent has two parts, like x to the third power. It has two parts. It has the base. This is the base. And it has a power. In this case, the 3 would be the power. Base 10, or decimal numbering system, means our place values are exponents with bases of 10. The ones place is 10 to the power of 0. The tens place is 10 to the power of 1. 100ths is 10 to the power of 2. And it keeps going. 10 to the third is 1,000. 10 to the fourth is 10,000. 10 to the fifth is 100,000. 10 to the sixth power is 1,000,000, and so on. Going the other way, 10 1/10th is 10 to the power of a -1. 10 to the power of -2 is 1/100th. 10 to the -3 is 1/1000th. 10 to the -4 is 1/10,000th. Well, if we have a really large or really small number, we often abbreviate it. We might have 5,200,000. We would often abbreviate it as just 5.2 million. Well, another way we could have abbreviated it, instead of writing out the word million, is we could have used the power of 10, 5.2 times 10 to the sixth. What's that? The million's way easier? Yeah. Well, obviously you recognize this as scientific notation. All scientific notation is a way of abbreviating numbers so they're shorter to write. Most of the numbers we're going to work with wouldn't really make sense to use scientific notation on them because they're small enough that we could just write out the full number. Scientific notation is used if you're way away from the decimal point. Like if you had a number with like 18 digits in it, well, it makes sense to use scientific notation so you don't have to write the whole thing out. But because I don't feel like writing out that long of a number, we're going to use smaller numbers as examples here. If I had something like 720,000, the way the scientific notation works is we take the first non-zero digit, in this case, it's the 7, right? We're going to put the decimal point after it and then list as many of the other remaining digits as we want to. There's only, the 2 is the only non-zero digit, so we'll just stop at the 2 here. Otherwise, you'd have to decide, am I going to go 2 or 3 more digits before I round it off, or how far am I going to go? And then I name the place value of that first digit that's in front of my decimal point. What place value is the 7 in? The 10 to the fifths. 100,000ths, or 10 to the fifth. So when we put a number into scientific notation, technically that is what we are doing. It works the same on the other side of the decimal point. If I have 0.0079, well, my first non-zero digit is the 7. So I'll write that as 7 point. My only other digit after that is the 9, times what place value is my 7 in? -3rd, 10 to the -3rd. So 7.9 times 10 to the -3rd. Now, you probably don't want to draw out your place values like this and label them every time you convert into scientific notation. So let's take a look at how we can do this shorter. So the 5,200,000 became 5.2 times 10 to the 6th. What most of you are probably taught for converting standard or decimal numbers to scientific notation was just moving the decimal point. Now, the decimal point starts out right there. I'm going to move this up a little. Starts out right here, and we want it to be after the first non-zero digit. We want it to be over here, so it has to move 1, 2, 3, 4, 5, 6 spots. So that's where this power of 6 on my 10 comes from. Now, it's positive 6 because this is a large number, and the positive power of 10 place values are on the larger side of the number line. You have to count the place values. If it's going to move here, you just count 1, 2, 3, 4, 5, 6 place values between there and where the decimal point is and where it was. So like the 0.0079, same thing. Count 1, 2, 3. We want the decimal point to end up there. So 7.9 times 10 to the third. This was a small number, so it has to be negative. It's in the negative power of 10 place values. So for this one, 0.000038. Well, we want the decimal point to be where? Between the 3 and the 8, so 3.8 times 10 to the what power? Yeah, it's got to go 1, 2, 3, 4, 5 spots. So negative 5 because that's a small number. Not quite though. You got to be very careful with that because it is only 4 zeros here. This one up here. That can work as long as you make sure you put that 0 on the front of it. So 910 million. Where's my decimal point going to go? 9.1, right? Yep. And 10 to the 1, 2, 3, 4, 5, 6, 7, 8. And going the other direction. Come on. Let's say we have 2.36 times 10 to the 4th. What's that going to be back in standard notation? Perfect. It's a positive power on my 10, so I know this is a large number. So I'm going to move the decimal point to make the number larger, and it's 4 spots. So I go 1, 2, I have to add zeros, 3, and 4. So you are absolutely correct. It's 23,600. Or I might have 8.04 times 10 to the negative 5. Same thing. I'm going to start with my 8.04. Does this number have to get smaller or larger? Yeah, it's a negative power, so this is going to have to turn into a small number. So we got to move the decimal point 5 spots. So it's right here. We're going to go 1, and then you're right. We have to add zeros. 2, 3, 4, 5. There's my decimal point. So 0.0000804. Now, I think I mentioned this before. Do we need the 0 in front of the decimal point? Mathematically, we don't, but most medical fields require you to put it there just for clarity. Now, in this one, with all these other zeros there, it's pretty clear there has to be a decimal point up there, but it's good to get in the habit of putting that zero before the decimal point. Okay, pages for you guys. We didn't get through everything, so we'll go back and review some of it next week if we have to. But you do have page 60 through 61, 1 through 47, the odds, and 61 through 65, the odds. That's more solving equations. They're a little bit more complex than some of the ones we did last week. Page 67 through 68, 1 through 27, the odds. Page 73, 1 through 39, the odds. A little bit of a review on percents. Again, we'll go over them more next week if we have to. Page 78, 1 through 35, the odds. And finally, actually, there's two more left. Sorry. Well, as a math teacher, if you still remember your friends and family, I haven't done my job. Just kidding, by the way. And finally, page 87 and 88, 1 through 39, the odds. Now remember, I'm not going to collect the homework and grade it. That doesn't mean go home and blow it off. But if you do a couple of the first ones, they're easy for you, please feel free to skip ahead to the more difficult ones and work on those. I'm not about you sitting at home doing busy work on stuff you already know how to do. Once you get to a point where you're confident you can do the most difficult ones, quit. I mean, homework is for you to learn. With that, anybody have any questions? Okay, you guys have a great week.